I'll give everybody a minute to get here. We'll get started here in a minute. I just want to give everybody a chance to arrive. All right. Let's just go ahead and get started here. So today we're going to talk about another data structure. This one is particularly useful sort of in a general sense. Hang on one second. Mark, I can do that. I can hear it. It's okay. Okay, I'm back. So hash maps are sort of useful in general. They'll pop up all over the place just in everyday programming. And they're incredibly useful because they allow quick access of data, as is sort of the theme of data structures in general. But in any case, a hash map is just a mapping from one data set to another data set. So for instance, this is a mapping from some food items to the type of food that they are. So a kiwi is a fruit, a cucumber is a vegetable, and chicken is a meat. And that's really all there is to the mental structure of these things. It's just a straight up mapping from one thing to another thing. And the things on the left here, the things that we're mapping from, are called the keys in the hash map. And the things on the right over here are called the values. So I mentioned, like, this is sort of a good mental picture for what hash maps are, but the actual implementation is sort of important here. If I just mentioned this, I think it would kind of be a short, it'd be a pretty short breakfast bash. So I'm going to go into a little bit more detail about how these things work on, like, internally, because on the outside they seem kind of magical. So ignore this, but inside of a hash map, what you have is actually an array of a fixed length. And the way that we map keys to values is we run them through what we call a hash function to determine their index, the index at which we should place the value in the array. So we come up with some hash function, and kiwi we find, when we run kiwi through the hash function, we get the index 5. We just get the number 5, and so at that point we place the value fruit. And let's go into a little bit more detail on that. So let's talk about hashing. This is the same picture as before. This is just an array of values, so it's an array, and we're storing some things in that array. But we need to figure out how these things, how we can get for example, where should we store fruit when we have the key kiwi? So the question is, how do we determine the index at which to place the value for a specific key? And the answer is that we need some sort of function to do it for us. And this thing has been looming down here because I forgot to delete it in the slides. It sort of hid from me. It was underneath the the area, the edit area when I was working on it. So, but this is the hash function that we're going to use. This is a Haskell function, but I think it's just the easiest way to explain kind of how this works. So there are a couple of things happening here. So we're going to hash a string, and to hash a string, we're going to first get the ASCII code of each character in the string. So that's a number. And then we're going to sum them. So we're getting a number here, and this number will probably be pretty big because ASCII characters get sort of large in the hundreds. And from here, after we take the sum of them, so we've got some number, maybe it's in the thousands, we're going to get the value mod 7. So mod is that a lot of people might know it as the parentheses sign in programming languages, but here in Haskell it's just called mod, and in math it's just called mod. And what it is if you take a number and you divide it by 7, it's the remainder. So this is going to clamp our value between 0 and 6 and give us an even distribution for any number of numbers. So that's good. That's what we want. So the reason that we do the mod 7 is because the reason that we have this hash function doing what it does is because it takes a string and it turns it into an integer that can fit an array of size 7. So this is going to give us an index. And an important note here is that this is not the only hash function that you can use. This is just one of many. It works for strings, but for example, it wouldn't work for an integer or a more complex data type. You can use, as long as you have a hash function that produces a value that can be used as an index in that array, you can use whatever you want. And so if you want to use a hash map to store, like, I don't know, like maybe order records or something like that, you can do that so long as you have some way of hashing your values. So I'm going to talk about the operations that we can do on hash maps, as is sort of typical of these talks. So the first thing that you can do is insert a value. And the key to all these operations is going to be that hash function that we talked about. So we're going to use the same one for each of these operations. We're going to use the hash function with the hash function that I just talked about. So say we want to associate rice with the food type grain. So the first thing that we're going to do is we're going to hash rice. So we're going to call that function that we had a second ago on the string rice. And that gives us 2. And so that's going to be the index that we place the actual value grain in. So we just put it there, it's done. It's a constant time operation because the hash function is very, very quick. I guess technically it's big O, the length of the string, but it's sort of negligible. These strings aren't going to get too long. So for all intents and purposes, you can write a hash function that produces a that is big O of 1, i.e. a constant function, and this will be for all intents and purposes a big O of 1 function, which is awesome. That's pretty much the best you can do. So for deletion, very similar process. We again hash rice, and we find that index 2, and then we just delete the value at this index. That's it. There's nothing there anymore. Then the last operation that I'm going to talk about is lookup. Again, it's very simple. We just take, so we're going to look up cucumber here. First, we just hash cucumber. We get 3. And then we return the value at that index in the array if it exists. And so we do, and we get vegetable, as expected. And I should mention that the way that I'm laying this out makes it seem like a very physical. It makes it seem like a very physical link, in the same sort of way that we've had singly linked lists and trees and stuff in the past. This link is very much not like, this doesn't even need to exist, essentially, this whole piece here, because basically when we hash Kiwi, regardless of what else is in this hash map, we're going to get 4, or we're going to get 5, and we're going to return that fruit. So this half on the left here of the hash map is sort of, you don't even have to store these values, is all really I'm trying to get at. You don't have to store them at all, because you use the hash function as sort of the mechanism for determining the value, which is awesome. So I was trying to figure out how to best show the use of hash maps in an application, and I think the best way to do this is actually through dynamic programming or something like that. Dynamic programming is this idea that you have these sub-problems that you need to solve, and they overlap. And when you're computing the result of something, you can kind of compute pieces of it at a time and then save them for later so that you don't have to recompute them. And this problem that I'm about to show you is somewhat, it's kind of like a very simple version of dynamic programming. And it's a little bit abstract, but I managed to find an XKCD about it, so it can't be that abstract. And I thought that that was like a good go-ahead for me. But the idea is this, and you can read this if you want. This thing's called the callout sequence. We have, this is a question taken from the website projecteuler.net, which is just this collection of pretty tricky programming puzzles. And this is the 14th one on that website. And the question is as follows. We have this sequence, it's called the callout sequence, and it's defined for the set of positive integers. So what you do is, if you have a number n, if n is even, then we divide it by 2, and then we continue on. And if n is odd, then we multiply n by 3 and add 1, and then continue on. So here's an example. If we start with 13, we multiply it by 3 to get 39, and then add 1 because 13 is odd to get 40. 40 is even, so we divide it by 2 to get 20, and so on. And the conjecture, the callouts conjecture, states that all numbers, every starting number ends up at 1. And the question here is, if we compute all of the callout sequences until they reach 1, starting from 1 and going to 1,000,000, which one produces the longest chain? So this chain contains 10 terms, but what about like 68? We want to figure out which starting number produces the longest callouts chain. So the problem is that 1,000,000 is a lot, and we're also generating sequences here, so we don't actually know how long those sequences are going to be in general. Brute force on this problem doesn't really work. It just takes too long to compute. I imagine that you could theoretically just run it for a long time. I don't think that this is one of those problems that will run like literally forever, although those do exist. But there's a way to do this efficiently with hash maps. So the question is, how do we make this faster? How do we avoid just stepping up from 1 to 2 to 3 to 4 to 5 and computing each sequence over and over again? So let's just look at that sequence that we had before. So we're starting at 13 and we're going down to 1. So the first thing that we need to observe is that really all we care about is the length of this sequence. This sequence is of length 10, and that's really all we care about because that's all the problem asks for. We want to know what the length of the sequence is that is the longest under 1,000,000. So the sequence starting at 13 has 10 elements in it. The length is 10. But the second observation that we should make is that when we compute this result, we're getting the results of every subsequence as well. So we know that, for instance, as a stupid example, the call-out sequence starting at 1 has length 1. And the call-out sequence starting at length 2 has length 2. And the call-out sequence starting at 4 has length 3. We can tell all of this just from computing the call-out sequence at starting at 13. So a wild idea appears. We have this sort of mapping here. I don't know, if you squint, you might be able to see it. So the idea is take n, the starting number, and map it to the length of the call-out sequence starting with n. So just as before, we had 13 down to 1. 13, the one starting at 13 has length 10, 40 has length 9, 20 has length 8, and so on. And this might start to take shape at this point. This looks like a hash map. It's exactly what we had before, except we're mapping numbers to numbers now. So hopefully that makes sense. I've just turned this on its side so that it looks a little bit more like what we've been working with before. So now I'm just going to sort of walk through the rest of the solution here, like why this matters. So we need to check the length of all sequences starting under 1,000,000. So what we're going to do first is just start at 1 and go up to 1,000,000. So I obviously can't convey this entire process in a 15-minute video, or any length of video for that matter. But we want to start at 1 and just compute the callout sequence and record its length. So eventually we're going to hit this example case here. So this was the case for starting at 13. But so later we're going to need to check for the length of the sequence starting at 40. So you can imagine, we step up from 1 to 2 to 3 to 4, we get to 13. When we get to 13, we can record all of the lengths of the subsequences that we compute. And then at that point, instead of computing the entire sequence for 40, which would normally take 9 steps, we only need to do a big O of 1 lookup in our hash map. So we get 40 is already mapped to 9 because every time we do one of these, every time we compute one of these sequences, we're storing the length of each subsequence in there. And this sort of just compounds. Eventually you're going to end up with a whole bunch of values in your hash map, or a whole bunch of keys in your hash map that correspond to these numbers that you're going to hit along the way, and a bunch of your computations are going to get cut short because they find a value in the hash map, and you can just take that number and tack it on to the length that you've already computed, or you might just start looking for something and you find it immediately, which is awesome. And that's kind of a big value of hash maps. There's a couple of things that I've glossed over here. Obviously, one of the major things is that there can be collisions. So two keys might map to the same index. And there are several ways of dealing with this problem. You can instead store a linked list in the value or in the array. So instead of just storing, for example, 6 here, we could store like 6, 18, 24, along with the keys. So you need some way to determine the keys. And that does, there's a drawback in performance from that, but it's sort of necessary. A perfect hash function doesn't exist. Another option is to take a key, hash it, and if something's already there, hash it again with a second hash function, and continue on doing that until you find an open slot. It's another option. And these things, I'm not going to go into too much detail there, but I did want to mention it in passing just because it is kind of, it's kind of hand-wavy to say that we have a spot for everything immediately available. But anyway, hash maps are extremely useful, not just in the context of like programming, puzzle programming, but JSON, for instance, is essentially just a hash map that has different types of values, but it just maps strings to JSON objects. So that's an example of a hash map. In PHP, arrays are essentially just hash maps in the same way, but they call them arrays. So yeah, I mean, they're extremely useful for mapping keys to values, and they can be very useful for speeding up specific types of computations where you have problems that you may have solved previously that you can just store the value of. Anyway, that's all I've got. Thank you guys for joining us, and I'll see you next time.